All right, I think I'm ready. Welcome back to everybody. We are almost done here. We have class, like regular class today and tomorrow, and then on Friday will be our test, which includes, just like all the other tests, it will include all of the questions, and then if everything is like going perfectly for you, you might be done at that point. Because you could, after that test, you could in theory have all of the items on your big list checked off. I think for almost everybody that will not happen, but and then the final exam will just be like one more shot at everything. So the test we're having on Friday and the final exam will be essentially the same thing, although I'm gonna rewrite all the questions. The final exam, you will have a full 3 hours to do it in. The one on Friday is just gonna be our normal class time. Any questions about that? I hope everybody knows what's up. Now, I have been looking at the list. Let's have a frank and honest discussion about the list. We are not going to get through everything on the list towards the end. So I hope that you have already crossed off the Selfridge-Conway method, which we skipped. I think all of this skipping topics is due to my trip early on in the semester. We lost some days. Okay, from the graph theory topics, we did this one, and this one, and this one, and this one. We skipped over Euler's sum of degrees theorem. It's pretty awesome, but there wasn't enough time, so you should cross that one off. For the sake of the questions on the test, I'm going to keep them numbered exactly as they are here, so there just won't be a question number 24 on the test. We did drawing Euler circuit and path. We did minimum duplication circuit. That was the last day before the break. Everybody was here on that day. Thank you all for coming. Draw a Hamilton circuit. We're skipping that. There's like 5 more topics. There's no way we're going to do them all in our remaining 2 days. I am going to try to do 28, 29, and 30 in our remaining 2 days. We are definitely not going to do 31. I'm not sure about 30. I suppose I'll tell you tomorrow. That's, tomorrow is the end of this. So depending on how far we get tomorrow, we might cut out number 30 or not. All right. So this is the new list. There will not be a question 19, 24, or 27, or 31 on the test. If this is unclear to anybody, or if you have somehow lost track of how many points you have on each one, let me know and I'd be happy to tell you. I am keeping track of them all in my computer. All right, excellent. Let's talk about these last 3 topics, 28, 29, and 30. So, today we'll do 28 and maybe a little bit of 29, and the next time we'll do 30. That's my plan, at least. We'll see how that goes. TSP. This is the name of a famous other graph theory problem. All of the graph theory stuff that we've been doing so far has been focused on Euler circuits and Euler paths, and that is about finding a route through the graph which covers all of the edges without repeating any. And then there was this minimum duplication circuit thing we did at the last time, and that's about covering all the edges and repeating as few of them as possible. The traveling salesman problem, that's what this TSP stands for. And this is another important, actually in real life, I think this is more important than the Euler business. The traveling salesman, this is just what it's called. The traveling salesman problem, and this is what on the big list, I call this TSP. And this, like I said, is actually super important in real life. I mean, this is not the kind of thing that like an ordinary person does in their ordinary life, but there are people, like big money people, who are very interested in being able to solve the traveling salesman problem. This is a classical graph theory problem, and I have a sort of real life word problem, I suppose. This is about me and my family traveling for the holidays. Are you ready for a cute little story? It's not much of a cute little story. This is a real sort of true fact about me. For Thanksgiving and not really for Thanksgiving, but for Christmas, it is important. You know, I have kids. I have my parents, and my wife has her parents. All of our, 4 parents, their grandparents are all still living. And, I mean the grandparents of my kids, which are my parents. Every Christmas, we got to visit everybody, right? All the grandparents want to have like their own Christmas thing at their own house. So, each Christmas, we must visit the whole family. They almost never come to our house. Why not? I don't know. We have a nice house. There's plenty of room. Every Christmas we must visit the whole family. And here is the arrangement. So here's like my house in Fairfield. I live in the town of Fairfield, Connecticut. I'll put a little star there. This is like my home, right? We have to visit my mom and dad. This is my mom and dad. They live in Boston area, Massachusetts. All right. We also have to visit. I'm making roughly a geographically accurate map, although it doesn't really matter. We also have to visit my wife's parents. So these are my in-laws. They live in New Jersey, Manahawkin, New Jersey, on the Jersey Shore there. All right, and then sometimes, not always, but let's just imagine, we also got to visit my wife's sister, Aunt Megan, and she lives in Pennsylvania. I suppose that's not an accurate picture of where Pennsylvania is. It doesn't actually matter. Somewhere like there, right? And the question that I have is, starting at my house and ending up at my house, what's the best route that I can drive to visit all 3 of these locations? All right? And you could imagine I could go sort of around in a circle like that, right? That's one way that I could do it. Or I could do something like here and then here. Well, that's just going around the circle the other way. I could also do something, I could do something like this, right? And maybe that's better for some reason. I don't know. So the question is, what's the best route to visit each location and return home? And by best, I mean shortest total distance. All right, this is the most natural way that you could talk about best. You could also talk about shortest total travel time, which is probably more or less the same thing as shortest total distance, although not quite, because you might think about you have to drive through New York City or whatever. Best, by best, I mean best means shortest total distance. All right. What's the best route to visit each location and return home? All right, this actually, the best way to think about this is in terms of a graph. So I'm going to write this as a graph. Now, in order to answer this question, you have to know, like, what are each of the distances from each place to each other place. But we are going to represent this as what we call a weighted graph. And I'll say what weighted means in a moment. Graph just means graph, but weighted graph is a graph which has some extra information in it. So I'm going to represent this information just by, there are 4 locations, and I don't even care about drawing this geographically accurately anymore. So I'm just going to say these are the 4 locations, and they are, I'll put them like this: Connecticut, Massachusetts, Pennsylvania, and New Jersey. All right, those are the 4 locations that we want to go to. We have to start and finish in Connecticut, but we have to visit the other 3 places as well. And I'm going to tell you what are the various distances from each single spot to another. So I looked these up on my Google Maps. The distance from the Connecticut location to the Massachusetts location is 156 miles. This is the actual distances from my house to my parents' house. Nana and Grampy, as we call them. From Massachusetts to Aunt Megan's house, this distance is 355. If we drive straight from Pennsylvania to New Jersey, that's 114. And if I go New Jersey to Connecticut, this is 152. Come on now. Sorry, my pencil just stopped. There we are. All right. This is actually part of why we decided to live where we do. It's because we are more or less the same distance to each of our grandparents' locations. All right, and then there's also, you could drive from Connecticut straight to Pennsylvania. So there's an edge that goes there, and that one, its distance is 194 if you do that one. And then there's also the other diagonal. You can go from Massachusetts to New Jersey, and that one, the number is 315. All right. Here I have, the edges are crossing in the middle, but the middle is not another vertex in the graph. That's just, the edges happen to be crossing over each other. All right. This is called a weighted graph. So the numbers here, the numbers on each edge are called the weights. And in this problem, they represent the individual distances from one spot to another. All right. Although you could use the weights to represent something else, like total time that it takes to travel or total cost of the tolls or whatever. Anyway, the numbers on each of the edge are called the weights, and that's why this is called a weighted graph. It's a graph which additionally has these numbers on the weights. And the question that we are trying to answer here is, what is the path? Well, really, I want a circuit. So this is what we call the traveling salesman problem. What is the circuit which visits every vertex and has the smallest total weight? That's what we're looking for. All right? A circuit which visits every vertex and has the smallest total weight. I'll just say this is very different from Euler circuits. Euler circuit is one which uses every edge without repeating any. And actually, I don't want to use every edge here. We are not going to use most of the edges, or a lot of the edges we're not going to use, right? Our goal is only to visit each vertex once. You don't have to use all the edges. So I will just say, we're not trying to use all the edges. That would actually be bad in this case. We're trying to make the quickest possible route that visits all the vertices. All right. We'll talk about how to figure this out, but maybe I'll just say at this point, this is super important in real life. There are like big corporations which need to solve this kind of problem every day. For example, I am imagining like the guy who's driving the Amazon delivery truck. They wake up every morning and their truck is full of, I don't know, like 100 packages maybe, and they have 100 addresses. And they have to just drive to these 100 different places in some order, in a way which, obviously, they want to drive this in such a way that they spend the least amount of time possible so that they can get the job done as fast as possible. So I will just say that solving this kind of problem, solving the traveling salesman problem, is super important for planning. I mean, this is just one particular example, but for example, planning delivery routes, right? The person driving the Amazon truck, like every day they have to do this for, I don't know, something like 100 different addresses. They have to figure out how, which order am I going to drive for these to do this in the most efficient way. Now, I happen to know the person driving the truck is not making this decision. The person driving the truck basically is just following instructions, and this calculation is done by a big computer somewhere. So solving the traveling salesman problem is super important for planning delivery routes, and you basically can't do this by hand because this is a hard problem to solve. It's hard, and big computers are necessary if you want to do this for a lot of locations. Now, in this example that I'm talking about, we have only 4 spots. It's not so hard to do this by hand. But in a bigger problem, like in a more realistic problem that you would want to solve in real life, big computers do this. The guy driving the truck, you would never make the person driving the truck decide on their own. The reason it's called traveling salesman problem is because, like, in the old days, this is the analogy that people made when they first discovered that this was an interesting problem to consider. If you have a traveling salesman, like a guy just sort of visiting house to house selling typewriters or something, like this is how they used to do business in the old days. And the traveling salesman has a certain amount of spots that he wants to hit, and he has to decide what order should I go to these spots. It's an important problem, and it's a hard problem to solve. If you were able to somehow figure out a way to solve this problem easily, you could immediately make a lot of money, because people like Amazon or different people who are interested in doing this kind of thing, it means a lot to them to be able to solve this problem efficiently, right? Okay, anyway, this is the question of the traveling salesman problem. And we ideally are going to talk about 3 different ways that you can approach this problem. Those were the 3 things on the list. We might only get to the first 2, but we are going to, for today, talk about the first one. It's called, so we can find the best route by, this is what is referred to as the brute force method. And this is the first thing that you'll see on your list. Traveling salesman problem, brute force. The brute force method is kind of like the stupidest way that you could think of approaching this, or it requires the least amount of big ideas. The brute force method is you just write down all possible routes, and then you find the one with the least weight. This is called brute force because you're not actually having any kind of sophisticated mathematical idea here. You're just saying, let's just try all the different ways you could possibly do it, and I'll choose the best one from the big list. Write down all possible routes, find the one with the least weight. So let's try and do that in my example. I hope you can still see this on your paper. I'm going to copy this down here. All right. So would you mind if I'm just going to, just for the sake of writing this in a compact way, I'm just going to call my 4 destinations C, M, P, and N, so that I can write them more compactly. But what we are looking for is, I'm going to try to do this, write down all circuits visiting each vertex, and I want to start and end at C, right? Connecticut, because I want to start and finish at my house. I'm going to write down all circuits which visit each vertex. So you could, I'm going to write sort of like a big list here. Maybe I'll go down, because I'm going to make some kind of a chart here. So these are the circuits. What I'm just going to write is like a list of vertices in order, and I have to start and finish at C. Now, just looking at the picture, you could, for example, go around, let's think about this. Actually, what are the various ways that I could go? I could start at C and go M second, or I could go to P, or I could go to N, right? If I go, maybe I'll just try and write these in a systematic way. I'll just try and write them sort of like in an alphabetical order. I could go C to M to N to P back to C. C, M, N, P, back to C. I just put it that way because that's like an alphabetical order. In fact, I could have written them just sort of like, I have to start and end at the C, but these 3 in the middle, they could be written in any order. If I put N, M, P, that would also work. I could go C, N, M, P, C. So that would be sort of going across this X. All right, so that, but anyway, I could go CMNP. I could also go CMPNC. Back that up. Yeah. Really, it's just a matter of writing all the possible orderings of those three middle letters. So you could put the M first in the middle, and then next goes N, or you could put the M first, next goes P. I could also put the N in that position, followed by M and P, or I could put the N in that position, followed by P and M, right? I'm writing down all the different ways you could write those three letters in the middle. The ones on the outside have to be C. But the three in the middle can go in any order. And there's two more possibilities. I could put P first, in the middle, P first, and then M, and then N, or I could put P first and then N, and then M, all right? Those are all of the possible ways to do a circuit which visits each vertex exactly once. You're not allowed to repeat any vertices. You don't want to, because you're trying to visit all the vertices once, all right? So those are the circuits. Now let's just decide what are the total distances for these. And this is a little bit annoying to do. You have to calculate the total weights. For these numbers, it's kind of a pain. You just have to add up the values. So I am going to look at these edges one at a time. C to M, that's this one, 156. So this is 156, and I'm going to add them up. The next edge here, M to N, is that diagonal one. That's 315. The next edge is N to P. That's up the left side, 114. And then the last one is P to C. That's the diagonal going down, 194. And these you add together. I did this on my calculator. I got 779, all right? That's how we do it, and we just have to do that 5 more times. Like I said, this is a pain to do. This is why it's called the brute force method. You're not actually having any big ideas. You're just doing the same thing over and over again. So the next one, let's do the next one. Maybe I'll just tell you the other answers after we do this one, because it's kind of a pain to do. Anyway, I go C to M first, which again is 156. Then I go M to P, that's this one across the top, 355. Then I go P to N, that's down the left side, 114. Then I go N to C, that's across the bottom, 152. Those, when I add them up, I get 777, slightly better. All right, and so on. Can I say, etc.? I'll just tell you what the answers are for the other ones. The next one is 1016. That one is quite a bit worse. The next one is 777. This is sort of a tie. The next one is 1016, and the last one is 779. All right, these ones I did ahead of time. All right, these are the 6 different total weights, and our job, what we're trying to do here is just to find the cheapest total weight. That would be 777, and also, I guess it's a tie, 777 here. So the cheapest total weight, which in our problem refers to the shortest total distance to drive. Cheapest total weight is 777. It was a tie between 2 of these circuits. Actually, you will notice something weird about these numbers. This is not a coincidence. There's 2 777s. There's also 2 779s and 2 1016s. Can anybody tell why? There's a reason for that. They kind of come in pairs like this. If you look at, for instance, the 1016s, they are this one, CPMNC and CNMPC. Can anybody see why? There's actually a reason why they have the same number that they add up to. You could look at them on the picture if you like. CNMPC goes like C, NMPC, right? That's that one, sort of a big X, hourglass type shape. Where's the other one? CPMNC. That's CPMNC, like that. Yeah?
Is it just because it's backwards?
Yeah, they actually are the same circuit. It's just one is written in the reverse order. All right. So these, you will expect these answers to always come in pairs. It's just a question of doing it in one direction or the reverse direction. So these come in pairs. Those two, and those two. These are in pairs by, can I just say something like the reverses, right? If you reverse one of the circuits, you will get one of the other circuits. So when I said you have to do this thing adding the numbers up 6 times, actually you don't. You only have to do it 3 times, and then you can already know that the reverse paths or the reverse circuits will have the same sums as the other one. So when you're doing this on your homeworks or on the tests or whatever, you don't actually have to do all 6 of them. You only have to do half of them, really, as long as you notice that the reversed ones are the same. All right, so anyway, the cheapest total route is 777. So the best route to drive is which one? So CMPNC. So that is, I should go to Massachusetts first, and then Aunt Megan's in Pennsylvania, then New Jersey, then back home. Or it's the same if you drive that same route, but in the opposite order, CNPMC. All right? There will always be a tie for best, because you can always drive the same route backwards and it'll be the same distance. All right? This is how we do the brute force algorithm, the brute force method. Any thoughts about that one? Questions? I got one for you all to try. So on our test, I'm not going to give you sort of big realistic numbers like this. I will more likely just make up some easy to work with numbers. So here is one for you all to try. Solve the traveling salesman problem by brute force in this graph here. This again is going to have just 4 vertices. I'll call them A, B, C, D. And the weights go like so. All right. And when I ask you to do this, I will usually tell you where to start and end. Let's just say I want to start and end at A. All right. So you should make a little chart like I did, which should begin by listing out the various circuits. And the first one could be something like, A, B, C, D, A, right? And then you have to write down, there will be 6 of them again, because there's always 6 when you have 4 vertices. Write down the other ones, and then add up the numbers.
There's only two, when you put B in this position, there's only 2 ways you can do that. So there is no other way.
Oh.
You could go A, C, and then there's 2 ways to start with A, C.
All right. Everyone seems to be doing all right. I'll write down what I'm getting here. Yeah, great. All right, can we chat about these? People are on their way. This, of course, it'll take you a few minutes to work out all the numbers, but I got 8 for the first one. That's because it's A to B is 3, and then B to C is this one, which is 2. C to D is also 2, and then D to A is 1. So that's 3, 2, 2, and 1. The next one, A to B is 3 again. So this is 3. B to D is 4. D to C is 2. And C to A is 5. When I add this, I get 14. You may have been writing these in a different order than I did, which is fine. You should get the same numbers eventually, although you may have them in a different order. A to C, for the next one, A to C is 5. C to B is 2. B to D is 4. And D to A is 1. So this adds up to 12. All right. I did 3 of them. I think actually this is all the adding that you really need to do. Remember what I said before? Because they come in pairs, this ACDBA is actually the same as if I read it in reverse, it would say ABDCA. That's this one. So I will expect those two to be the same as one another. If you like, you can carry through all the numbers, but I already know this one also must be 14 because it has to match that other one. All right, and if you're doing this on homework or on the test or something, I would expect you to take this little shortcut. This one here, ADBCA, ought to be the same reading backwards, ACBDA. That's this one right there. So this one is also 12, and that means the last one will pair up with the first one, which was 8. I mean, in mine, they pair up in this order, although if you wrote them in a different order, they will pair up in slightly different ways. Okay, anyway, the best one is 8, and so the best solution is the first, I guess it's the first one that I wrote, A, B, C, D, A, or in reverse, A, D, C, B, A for 8. 8 is the total weight of that. All right. This is how we do the brute force method. Any questions about that one? I would say this is kind of annoying to do. It'll take you a few minutes, but it doesn't involve any big ideas. You just have to write it all down and work it all out. That's why it's called the brute force. You're not actually using some kind of smart thinking. You are thinking harder, not smarter. All right? Great. This is the brute force method. Now, I will say the brute force method is fine. Like, I can do this give me a couple minutes and I can work it out. That is, when there are 4 vertices, this requires, for 4 vertices, this requires checking 6 different possible circuits. Really, it's only 3 because you can pair them up, but when you make your list, there are 6 total circuits that you could possibly do here. For more vertices, it's way more though. If I'm using 5 vertices instead, it means I have to write in the middle here all different reorderings. Like here, I'm writing all different reorderings of the 3 middle guys. But if I have 5 instead of 4, you'd have to write all different reorderings of the 4 guys in the middle, which is a lot more. Actually, I happen to know that's 24 different. For 5, you would have to check 24 different circuits, and for 6, you would have to check a lot more. I'm not sure what it is. It'd be something like in the mid 100s. This number, this gets very large for many vertices. And in fact, if you're talking about like a real life situation where you'd want to do this, like the guy in the package truck who has to deliver 100 packages, if you have, for say 100 vertices, this brute force method is simply impossible to do, even if you're using a computer. This is way too many different possible circuits to check. So for 100 vertices, the number to check is far too big, even for computers. All right. So the moral of the story here is the brute force method, it does work, but if you're trying to do this in real life on a like realistic problem in the real world, it's probably not going to work to do the brute force because it's just too much calculations. You definitely would never want to do it by hand, but even if you're using a computer, it's too much calculations to be able to do it. So for this reason, so the brute force can't be used in, I will say, large scale, real life traveling salesman problem solving. All right, but these problems, we still have to do them in real life. Like the guy driving the package truck somehow has to figure out what's the best route to drive. And the fact is, actually, this is, I don't know, this was kind of surprising to me when I learned this, but this is a true fact. The guy driving the package truck is not actually driving the best possible route. And that's because this is too hard of a problem to solve, even using the biggest computers in the world. So I will just say, turns out, nobody knows how to find the best traveling salesman problem solution in reasonable computing time, right? In theory, you could always solve it by the brute force, but if you're doing this with like 1,000 different locations, it might take you a year to compute the answer with a computer, which is not good enough because you've got to do this like every day on the package truck, right? So it turns out actually nobody knows how to find the best traveling salesman solution in a reasonable amount of computing time. If you could somehow find a method which always gives you the best route for a lot of vertices in the graph, you could become a wealthy individual. Like there are real people with lots of money who are very interested in knowing how to do this. And as of today, nobody actually knows how to do this in an efficient way. So, but of course, they still got to drive the trucks every day. So what do they do instead? Nobody knows how to find the best traveling salesman solution in reasonable computing time. Instead, they use what we call approximate algorithms. Algorithm just means like, well, it usually these days means like a computer program, but it just means a way of solving a particular specific problem. They use approximate algorithms, that is to say, methods which give pretty good routes, perhaps not actually the best possible. All right. So the guy driving the package truck is actually not driving the best possible route, because that's actually impossible to calculate in a realistic amount of time. And since they have to do this every day, they're not going to be crunching the numbers in order to do this every day. Instead, they are using approximate algorithms. That is, there are methods which give you pretty good routes, maybe not the absolute, like mathematically best possible route, but they're driving routes which are pretty good, maybe not the best possible. And we are going to talk about two such ways to do this. We got 8 minutes remaining. Maybe we can talk briefly about the first one. So let's talk about one approximate method. That is, this method is not meant to give you the best route every time, but it's meant to be way easier than the brute force. That's the idea. This is called the nearest neighbor algorithm. All right. So the whole point of this method is it may not actually give the best route, but it's much faster to do, much easier to calculate. Even if you had 1,000 different spots to visit, you could actually do this by hand. I don't know about 1,000, but if I had 50, I could easily do this by hand. It's much easier to calculate than the brute force, and that's why it's useful. Here's how it works. It's fairly easy to describe. Let's just do the same example. This is not the same example, sorry. This is a new example. This is a weighted graph. Again, I'll just call them A, B, C, D. How about weights like so? All right, these are the weights. And we want to find a pretty good circuit which visits all the vertices in a way which doesn't require that we calculate every possible thing and just add them all up, because that will take too long. All right. The idea is, so let's start and finish at A. And this is called the nearest neighbor. I'm going to write NN. The nearest neighbor procedure, the nearest neighbor algorithm, here's how it works. So you just sort of start at the starting point, and I'm not going to try to consider all possible routes. I'm just going to choose one route as I go, and as I go, I'm just going to choose the cheapest possible edge that's available to me at any time. So you start at the start, which is A in this case. You start at the starting vertex, and then choose edges as we go. You are not going to try to somehow consider all possibilities. You just make it up as you go. Choose edges as we go. Each time, choose the cheapest available edge. All right. And by available, I mean you don't use one of the edges that you've already used. And also, you're not allowed to use an edge which goes to a vertex that you've already visited. So by available, I mean only use edges to vertices we haven't already visited. And I also mean don't finish early. Like we're starting at A here. Don't go back to A before you've hit all of the other vertices, all right? But anyway, this is the nearest neighbor algorithm. So in this example, this is pretty easy to do. We start at A. All right, this is, I mean, basically you can do this in your head, but I'm going to try to write down narrating what I'm doing here. Where should I go first? From A, my choices are I could go to B or to D or to C. Which one should I do?
B.
You should go to B. This is what I said. Each time choose the cheapest available edge. So if my choices are B to D or to C, that's a 1, a 4, or 5. I pick the 1 because that's the cheapest of those possibilities. So I start at A and then go to D, no, B. This is weight 1. It's called the nearest neighbor because if you imagine those weights represent distances, I'm going to the one which is nearest to A, which is B, distance 1.
Do you have to write it out like that, or can we just say?
No, so I'm writing this out just so that you can follow what I'm doing. But when you're doing, if you know what you're doing, you can basically do the whole thing in your head. So my circuit shall be A and then B. And then I ask, from B, where should I go next? And it would be helpful while you're doing this to kind of like, maybe you could just sort of like scribble on the graph to say, I just picked that edge. Okay, my next choice, I'm not going to go back to A, but I am going to go down across to C. That's because from B, my two choices now are the 1 or the 2. I should pick the 1 because my strategy is to choose the cheapest available edge. So then C, that's this diagonal. I'll scribble that one in. All right. Now I have to choose the cheapest available edge from C. I could go up for 5 or across for 3. I choose the 3. Actually, I shouldn't go up for 5 because that would make me finish early anyway. So I will go across the bottom for 3. So I'm going to go to C, then D, across the bottom for 3. And then from D, my options are 2 or 4, but the 2 is sort of off limits to me at this point. You can't go up the 2 because I'm not allowed to revisit B. So I must take the 4 at the end to go back to A. A, B, C, D, A is the route that I get. All right. And what's the total? So the circuit that I get is that one. And the total weight here is 1 plus 1 plus 3 plus 4. Those are the edges that I used. And if you add those up, you get 9. All right. And it turns out actually in this example, that actually is the best route that you could possibly find. If you go through the brute force, you could check all 6 of them. This one turns out to be the best. This is the best route. In general, though, this doesn't always give you the best route. This is kind of like in life. It's like life is made up of, making a series of individual decisions. If you always choose the easiest route in every individual decision, this is not always best for you. Sometimes you have to look at a bigger picture or something. But anyway, in this example, that's the best route. More on this next time, and then hopefully we'll get to the sorted edges. That was the other one.